Section 11.4, integrated rate laws. So, integration, right? Calculus, Newton v. Leibniz. There is a great epic rap battle of history with Newton versus Bill Nye at that link. Hilarious. It has Weird Al as Sir Isaac Newton. So let's look at our integrated rate laws. So in our integrated rate laws, what we're going to do is we're going to take that form of the rate law that we had before, and then we're going to throw it through the calculus machine and integrate it. So we're going to be able to look at how those concentrations are changing with respect to time. Or if I've got a given concentration to start with, at how long will it take to reach a new concentration? So that's what our integrated rate laws are going to do for us. Let's look at our first order rate laws. So in a first order reaction, the rate of the reaction is going to depend on the concentration of the reactant to the first power. So for a chemical equation in the form where A is going to go to some products, where the kinetics are first order in A, the rate law is going to be rate is equal to minus the change in A with respect to T, delta T, or K times the concentration of A to the first power. Remember, there's a minus in here because this number here is going to come out as negative when you do your final minus initial concentrations. All right, so if I take this, right, and I integrate it, well, I'm going to end up with my integrated first order rate law, which says that the natural log of A, the concentration of A, is equal to minus K times T plus the natural log of our initial concentration. Right? So this K over here, right, that's just this K, this reaction rate constant. Right? T is going to be our x-axis, so if you want to think of this as y is equal to mx plus b. Right? Our intercept is our initial concentration. Our slope will be negative k. Our x-axis will be time, and this is going to be natural log. Right? And so remember, when we looked at our raw data, it kind of looked like that, where we've got time on one axis and concentration on the other, and it's definitely not a straight line. Right? It's going to follow one of these natural log functions, hence the natural log part. Right? What's nice about this is that you can say, well, given an initial concentration, after 30 seconds, what's my new concentration? Or you could say, well, how long would it take me? Now I can say, well, given 30 seconds, what's my new concentration? Or I could do it the other way and say, well, it's been 3 minutes, or I want to take it to quarter of my initial concentration. How long will that take? So we can go either way on that line. So like I said, this is going to be a y equals mx plus b kind of line. Right? So the equation shows how the concentration depends on the time. If the initial concentration of A and the rate constant K are known, then the concentration at any time can be calculated. It's in the form of an equation y is equal to mx plus b, which you guys are all familiar and comfortable with, where a plot of y versus x is a straight line with a slope of m and an intercept of b. So y is equal to the natural log of A, x is equal to t, m, our slope, is negative k, and b, our intercept, is the natural log of our initial concentration. For the reaction AA goes to products, the reaction is first order in A if the plot of the natural log of concentration of A versus T is a straight line. So if I had my first order reaction, it's going to give me a nice straight line. My 0th order reaction is going to be some sort of non-straight line. And my second order is also going to be a non-straight line. So it's, if you plot this where it's natural log of A versus time, and you get a straight line out, that's one of the ways that you know you've got something that is first order with respect to A. So this is that second type of experiment where you collect a lot of data, you figure out graphically which reaction order you've got. Right? So the integrated rate law for a first order reaction can also be expressed in terms of the ratio of A relative to its initial concentration. Right, so you could say that the natural log of our initial concentration divided by our target concentration at time t is just going to be equal to K times T. And it's the same equation, we're just rearranging it. Check on that formula sheet to see which one they give you. If you're more familiar with or find it easier to work with one form of the equation versus another, it might be worth your while just to memorize some of those. Right? So let's look at the decomposition of N2O5 in the gas phase. Right? And it's studied at constant temperature. You're going to take two N2O5s and you're going to decompose them into 4 NO2s and some oxygen gas. So this is our raw data as concentration and time. So as our time goes on, our concentration drops. Just kind of looking at it, it's hard for us to see what's happening. We can tell it's not constant. We can tell it's decreasing. If we looked at it like, okay, the change between here and here is probably bigger than the change between here and here, but it's hard to tell exactly, right? So using these data, we want to verify that the rate law is first order with respect to the N2O5, the dinitrogen pentoxide, and calculate the value for the rate constant, where the rate is going to be minus delta N2O5 over dt. Right? So we're going to take our data, we'll take the natural log of our data, our concentration, we'll keep time the same. We plot it up, we get a nice straight line. Right? Remember that our intercept B is going to be minus the natural log of A at time 0. And the slope is going to be equal to minus the rate constant K. The values of the natural log of the dinitrogen pentoxide concentration at various times given in the table above show in the plot for the natural log of the N2O5. The fact that the plot is a straight line confirms the reaction order is first order with respect to the dinitrogen pentoxide, and since it follows that the equation is going to be the natural log of N2O5 is equal to minus KT plus the natural log of the initial concentration. Since the reaction is first order, the slope of the line is just going to be change in y divided by change in x, or delta y over delta x, or the change in the natural log of the N2O5 over the change in time. So in other words, you can pick one of these and one of these, get a delta, and the corresponding x values and get a delta x. Right? If it's a nice, neat straight line. It is better to go with a linear least squares plot, if you can, rather than arbitrarily picking any of those two data points, because what if this one over here, this first one, is kind of a little bit weird. Right. So, our slope is just going to be change in x over change in y over change in x, or rise over run. Since the first and last points are exactly on the line, we're going to use those to calculate the slope. So they put in their final and initial concentrations and the final and initial times, and they end up with minus 2.77 molar divided by 400 seconds. So minus 6.93 times 10 to the minus 3 per second. So our slope is going to be 6.93 times 10 to the minus 3rd per second. And that's really an awkward way to do it. In the lab, you just grab a slope from Excel. On paper, you just use the regular equation to solve for your unknown K. All right? Let's look at first order rate laws part 2. So using the following data, calculate the concentration of N2O5 at 500 seconds after the start of the reaction. So just kind of eyeballing it. All right, so now we're going to use our first order rate law. So at 150 seconds, we know it's going to be somewhere in here, right? So somewhere between 0.05 and 0.025. Your gut instinct is saying it's going to be in here because your rate is going to depend on the concentration. It's probably going to be a little closer to 0.05 than it is to 0.025, right? But it should be somewhere in there, right? So we know that our concentration of N2O5 is going to be 0.05 moles per liter at 100 seconds. And we know that our concentration is going to be 0.025 at 200 seconds. Since 150 seconds is halfway between 100 and 200, it's tempting to assume that we simply use an arithmetic average to obtain our concentration of N2O5 at that time. But that's incorrect because it is the natural log of the N2O5, not just the concentration of the N2O5. So you have to account for that being natural log E. So it's directly proportional to T. Right? It's our natural log, not our just concentration. Okay? So use the following equation to calculate after 150 seconds, given a calculated K that we would have gotten from our slope before, and an initial concentration. So if we looked at this graph here, right, we've got 1 point where time is 0, and we've got a concentration that is known. And we've got a slope over here, m. So this would be our point slope formula for those of you who are keeping track with the algebra and the geometry at home. So really, we're just going to take it, plug it into our integrated rate law. We're trying to solve for this, our concentration at a given time. We know our slope, we know our time, we know our natural log of our initial concentration. So time is 150 seconds. Our K value is 6.93 times 10 to the minus 3 per second, and our initial concentration is 0.1. Right? So we're just going to replace those values in, right? So we've got the right-hand side, right, where we've got our K, T, and B. We make the math happen. We're then going to take this, we're going to end up with the natural log of the N2O5 concentration on the right. We need to get rid of it, so we're going to take the anti-log, so e to the minus 3.3, and we're going to get a value of 0.0353. So where does it show up? Well, it's not exactly halfway in between. It's a little bit closer to the 0.05 than the 0.025. But it is going to be halfway in between. So, like, it's not going to be up here at 0.06. And, it's not going to be down here at 0.02. Right? Something that is very useful is what's called the half. So just like in the Henderson-Hasselbalch, where you had a special point, where you're halfway in between your equivalence points, so your moles of base were equal to your moles of conjugate acid. Our half-life is just a specific case of the integrated rate law where our concentration is going to be 1/2 the original concentration. So if we looked at this, right, and this guy was like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this guy started off at 10. It's where this guy is 1, 2, 3, 4, 5. Right? So that's where it's 1/2 the concentration. So if the reaction is first order in A and we've got this general form, we know that this guy is going to be 1 and this guy will be half of that, 0.5. Right? When we take that and we range it, right, we're going to say that our concentration of A is going to be equal to our initial concentration over 2. That's what it means to be at half the concentration. So our integrated rate law becomes the natural log of our initial concentration divided by our initial concentration divided by 2, which is equal to K times the half-life, or the natural log of 2, right? So this 2 kind of moves up to the top. So the natural log of 2 is equal to KT times 1/2. And that's our half-life equation, which is just a special version of our integrated rate law. So substituting that value of ln of 2 in there and then rearranging it to solve for T 1/2 gives us the general equation for computing what the half-life is for a first order reaction. It comes out as 0.693 over K. So for a first order reaction, the half-life does not depend on the concentration. So our half-lives are going to be steady over time. All right, so let's look at our original raw data here. So at T0, Right? We're going to start off with 1 molar. After 1 half-life, right, we've gone to half the concentration, so it's 0.5 molar. Right? And let's say it takes 100 seconds for us to do that. To go 2 half-lives, right, we're now at 1/4 the concentration, so half of a half is going to give us 0.25. Right? And notice that this difference between here and here is 100. And the difference between here and here is 100. And the difference between here and our third half-life, where we've got 1/8 the concentration, 0.125 molar, is also going to be 100. So our half-lives are evenly spaced out for a first-order reaction. So sometimes if you've got data and you're like, oh, it's curvy, if you can kind of figure out where half is and then 1/4 is, you can probably look at that without having to go through the whole, I'm going to take a natural log, right, and then plot it up. It's the ln of the concentration versus time. So if you know your half-lives are evenly spaced, it's first order. That's just a pro tip. Right. Let's look at some first-order reactions. So a certain first-order reaction has a half-life of 20 minutes. Calculate the rate constant for this reaction. How much time is required for this reaction to be 75% complete? So first we're going to solve the equation to find out what K, our rate constant, is. So we took that formula where K is 0.693 over T1/2. We know that our half-life time is 20 minutes, and we know 0.693 is always 0.693, the natural log of 2. And so we rearrange and we end up with K being 3.47 times 10 to the minus 2 per minute. We're then going to take that integrated rate law again. We're going to plug this value in here. Okay? So for our reaction to be 75% complete, 75% of the reactant has been consumed, leaving 25% in the original form. Right? So what's my ratio? Times 100% is 25%. So my A over A0, my target concentration over my initial concentration, is going to be 0.25. It's 25% left. Right? Or if we're going to express it this way, we'll do 1 over 0.25, which is equal to 4. Right? Why would we do it this way with the A0 on top? Because if we look over here at our formula for integrated rate law, it says natural log of A0 over A at a given time. Right? So we want our A0 on top. An easy way to do this is like, that's 2 half-lives. Right? So we're going to estimate that this guy's being 2 half-lives because right back here we had 50%, 25%. Right? So our 25% should be 2 half-lives. So it's going to be the natural log of 4 is equal to K times T. Right? We've got our K value in here that we just calculated. We want to make sure that these units match. Time cancels out time. Right? Notice that there is no unit over here. This matches the fact that our natural log can't have a unit. Rearrange it. We get T is equal to the natural log of 4 over 3.47 times 10 to the minus 2 per minute, 40 minutes. And is that 2 half-lives? Nod your heads up and down. Yes, indeed it is. 2 half-lives. So thus it takes 40 minutes for this particular reaction to reach 75% completion. This problem can be solved using the definition of a half-life instead. So after 1 half-life, the reaction has gone to 50%. If the initial concentration were 1 mole per liter, after 1 half-life, the concentration would be half a mole per liter. If 1 more half-life would produce a concentration of 0.25 moles per liter, 3 half-lives would leave 0.125 moles per liter. Right, or 1/8 our initial concentration. So if we compare 0.25 moles per liter with our original 1 moles per liter and shows that 25% of the reactant is left after 2 half-lives, that's a general result. 2 half-lives for this reaction is going to be 2 times 20 minutes or 40 minutes, which agrees with our preceding answer. All right. Second order rate laws. Still in 11.4. So our second order rate laws means that we're going to start off with K is A squared, or it could be A times B, but we're going to go with A squared just because the math looks it's a little kinder to look at the math. Doubling our concentration of A means that our reaction is going to happen 4 times faster. So our reaction quadruples the reaction rate. Tripling the concentration of A is going to increase the rate by 9 times. So 3 squared is 9. For the chemical reaction, A goes to the products. Where the kinetics are second order, our rate law is going to be our rate. As our change in A per change in time is going to be K times A squared. If I take that and I go through and I Isaac Newton that up, my second order rate law is going to have the following form, where it's 1 over A is equal to KT plus 1 over our initial concentration. Time is still the same, but now we're manipulating our concentration and we're doing 1 over A. And it's still going to give us something with a y equals mx plus b type of form. Right? Here we've got our y value. That's 1 over our concentration. Our slope is still going to be k, but now it's going to be positive k. We've got some intercept. Right? It's going to be 1 over A versus natural log of A. And t, that's still going to be our x coordinate. So time is going to be x. When we do that, we're going to end up with a straight line where the slope is equal to positive k. This equation shows how A depends on time and can be used to calculate the concentration of A at any time t, provided k and our initial concentration are known. Right? When 1 half-life of the second order reaction has elapsed, so we're going to do the same sort of thing that we did before. We're going to take our A concentration at 1/2. That's going to be 1/2 of our initial concentration. So it's going to be 1 over A over 2 is equal to KT 1/2, which is equal to 1 over our initial concentration. Do a little bit more rearranging. We'll get 2 over our initial concentration minus 1 over initial concentration is equal to KT. Or we can write this out as 1 over our initial concentration is equal to K times RT 1/2. Flip these guys around so we can get this the T, and we'll end up with T 1/2 for a second order reaction is going to be 1 over K times our initial concentration. So in this case, each successive half-life is also going to be halved. So our half-lives will stretch out. Our half-lives will increase over time. So if we look at our initial plot, or original plot where we've got time and just concentration, right? If we had 1, a half, and our second half-life, and if our first half-life took us 10 seconds, our second half-life is going to take us 20 seconds. And our third half-life should take us 40 seconds. So our half-lives are going to stretch out if we have a second order reaction. Again, you can kind of look at that and say, okay, if I can measure where my half-lives are, might have a second or a first order, where my second is going to flatten out faster because my half-lives stretch than it would with my first order. So here's an example. Butadiene is going to react to form its dimer according to the following reaction. So we're going to take 2A and we're going to form B, our product. So if following data is collected, we're starting off with no product. We're going to get some product forming in over time. Right? We've got all of this data. How are we going to look at that? Well, we're going to ask ourselves, is this reaction first or second order? What's the value of the rate constant for the reaction? And what's the half-life for the reaction under initial conditions for the experiment? Half-life's kind of easy because like you could go through and you're like, okay, well, how am I going to go from here to half of that, 0.005? So you can kind of guess where that half-life is, but we're going to do it mathematically. So our solution, right? A, graphically determine it. So to decide whether the rate law for this reaction is first order or second order, We're going to see whether the plot of the natural log versus time is a straight line for our first order, or the plot of 1 over the concentration is a straight line for our second order. So we got two sets of data. Time is the same. We'll do 1 over and we'll do natural log. The 1 over is going to be for our second, and our natural log is going to be for our first. So we're going to take these guys, we'll plot them up. All right, so for our first order, where we're looking at the natural log, it's a curvy line. For our 1 over, right, where we're looking at a second, it's a nice straight line. So of these, it is going to be a second order reaction, right? Which one's giving you the straight line, right? If I did 1 over it, it's going to be a second order. Since the natural log plot versus time is not a straight line, the reaction isn't first order. The reaction is second order, as shown by the linearity of the 1 over the concentration versus time. So we can rewrite the rate law for this as a second order reaction as saying rate is equal to K times our concentration squared. In that second order reaction, if we take our plot versus time to produce a straight line slope K, in terms of our standard equation, y equals mx plus b, y is going to be 1 over the concentration, and x is going to be time. And the slope is going to be change in y over change in x, or if we just look back over here, what's this got to be? It's going to be plus k, right? So for a second order reaction, this is going to be our calculation for the slope. Using our points at t0 and t6,200, we can find the rate constant k, and just plugging in two different values, doing rise over run. Our slope is going to be 381, right? Our two concentration differences and our two time differences over 6,200 seconds. Again, check the units on things like this. They might throw you something in minutes. If you've got a half-life for something like carbon-14, that could be in millions of years or hundreds of thousands of years, depends on what the half-life is. So make sure you check those units, especially with the half-life-y things. So you end up solving what that slope is, 6.14 times 10 to the minus 2. And again, this is molar to the minus 1 seconds to the minus 1. The expression for the half-life, if we're going to do this, same sort of math again. So our T1 half is going to be 1 over K times A. So, you might want to rewrite this, all of those equations, and I think I got another slide where it shows them all separate. So you could think of this as K times 1 over A, right? Where you're separating out your M and your X again, right? So we know we got our value for K. We're going to solve for our T1 half. Our initial concentration of C4H6 is halved at 1,630 seconds. All right, so once we get our K, we can figure out what our T1 half is, given this and given our initial concentration. All right, so let's compare. In our first order reaction, T1 half depends only on K. In our second order reaction, our half-life depends on both our concentration and K. Our half-life is constantly spaced out, whereas in a second order, our half-lives are increasing over time. Right? What about 0th order? Yeah, you can do it, and 4th and 5th and 6th orders, you're just going to continue your integration. For a 0th order, it's got a rate constant that doesn't change with concentration, so our rate is just going to be K times A to the 0, which is K times 1 or K. So our integrated rate law is just going to be concentration of A is equal to minus KT plus our initial concentration. So our regular old plot, right, just our data where you've got the concentration of A and you don't change it, gives you a straight line. That's 0th order. So to graphically determine if you've got 0th order and you plot up your raw data, A, concentration of A versus time, that's a straight line. For first order, it's a natural log as a function of time. And for second order, it's going to be 1 over the concentration as a function of time. Third order would be like 1 over the concentration squared, but we ain't going to worry about that. So an expression can be obtained for the half-life of that too. So again, our half-life is going to be 1/2 our initial concentration, and our half-life time is going to be some value that we're going to solve for. So initial concentration over 2 is equal to minus K times T 1/2 plus A naught, or, right, we can say KT is equal to 1 over our initial concentration divided by 2K, or we just simplify it as T 1/2 is our initial concentration over 2K. So how are you going to differentiate between these? 0, first, and second order rate laws from their graphs. Right? Depends on what you put on the axis. They're all going to have T on the bottom. 1, first, second, 0, 1, 2. Right? This guy's just going to be our concentration. This guy's going to be for the first order. It's a big one. Natural log. And for our second order, it's going to be 1 over the concentration. Whichever one is going to give you the straight line is going to tell you what your reaction order is. All right, so our integrated rate laws, if you got more than one thing, so now we're going to get into multiple reactants, you're going to be treated by choosing conditions so that the concentration of only one reactant varies in a given experiment. So what you're going to do is what's called pseudo order reactants. Basically, you're going to set one of those values either so high or so low that its value doesn't change very much. That's done by having the concentration of one reactant remain small, while the concentration of all the others are going to be changed. And it's going to cause this rate law to what we call reduce. So if our original rate law is K times A to the N times B to the M times C to the P, right, our reduced rate law is going to be K prime times A to the N. So what we'll do is we know that K prime is going to be K times the concentration of B to the M and C to the P. But our concentration of B is going to be way, way bigger than our concentration of A. And our concentration of C is going to be way, way, way bigger than our concentration of A. So what you do is you do the same sort of thing that you would before. Now you're still going to make a plot where you're going to have, here's my time, and here is my concentration of A, and it's going to change, right? But you've got some concentration of B that is way up here in the stratosphere. And so even though this guy might be changing by, 0.5 molar, if this guy's up here at like 1,000 molar, and over time it changed to 1,000 minus 0.5, did it really change much? No. So you basically make the concentration of B and C so big that it doesn't notice, right? So by analogy, right? Like if I go into my bank account, I'm going to notice, right, if I went from $100 in my bank account down to 50. Now, is Bank of America going to notice if they're suddenly $50 short? Right? They're not going to notice. It's not even going to show up on their radar, right? In terms of like the billions of dollars that they have, if they're plus or minus 50, no big deal. For me, if I only start off with $100 in my bank account and I gain or lose $50, that relative change is very noticeable. And that's just the trick that you're playing, right? So the value of N is going to determine whether A is then going to, with this plot, give us our manipulated data for a straight line. If I do 1 over, it's going to be second order. If I do natural log, it'll be first order. If it's a straight line from the get-go, it's going to be 0th order. The value for K prime is determined from the slope of the appropriate plot. So if we did this, right, we had a concentration of A, and it was like 1 over A, right, and that was our straight line. Well, that would be our second order. Right? And then what you do is you set A really high and don't change it, and you let B vary. And then you set C and A really high, and then you let B change. And you set A and B really high, and you let C be the one that changes. Right? So you're just going to change those a little bit. So I like this table because I think it sums up very neatly your different reaction orders, what the corresponding rate law is, what the units of K are, what the integrated rate law is, which one gives you the straight line plot, and what our expected half-life expression is. Right? So this kind of summarizes all those things up. And if I'm remembering right, we give you like the integrated rate laws on that sheet. But hey, it's sometimes useful to know what these things are. So this is a good spot to like stop, study, write this down in your notebook so that you know what's going on.